Hey, so now I'm going to continue. I'm going to give you guys some numeric examples of derivatives of those trigonometric equations, right? So let's see here. So it's going to be like two simple exercises. Let's say that y equals x minus the tangent of x. So we're going to take the derivative of this with respect to x. Okay, just going to derive this thing here. Yeah, we're just going to derive. I'm just going to do this. That's going to be the notation that I'm checking the derivative. So the derivative of x with respect to x, I'm just going to put dx in. So it's going to be 1 minus the derivative of the tangent is the secant squared. Secant squared of x. That's it. Okay. Now another one is y equals x secant of x. We're going to take the derivative with respect to x. So here we got to use the product rule because you got a function here and a function here, and they're multiplying, right? They're in a product. So I'm going to take the derivative of the first one, which is x. So it's going to be just 1 times the second. So it's secant of x plus the first times the derivative of the second, and the derivative of the second, the secant of x is secant tangent. So it's going to be secant of x tangent of x. And that's it. You can factor out the secant here if you want, like secant of x, and then you multiply this by x. No, yeah, but 1 plus x tangent of x. And that's it, but you don't have to. Now, I'm going to talk about the chain rule, okay? The chain rule is, it's like a bunch of gears. So if you have one gear, small gear, that moves a second gear, that second gear is going to move a third gear, and there's a ratio between the gears, okay? So let's just say that the first gear moves in one rotation, it moves only half a rotation in the second gear. So when the first gear rotates once 360 degrees, the second gear is just going to rotate 180 degrees. And let's say that the second gear rotating once rotates the third gear only half. So when the first gear rotates 360 degrees, the second gear is going to rotate 180 degrees, and the fourth gear is just going to rotate 90 degrees. Okay, the third gear is just going to rotate 90 degrees. So that's the chain rule. It's like a bunch of gears, and it's something like this. Let's say that you have y equals f of g of x, okay? How do you take the derivative of this stuff? Well, you can replace, you can put it down here that u equals g of x, okay? And then this is going to be the f of u. But here's the thing. You want to take the, okay, so this equals f of u. Now take the derivative of this with respect to x. So you're going to take the derivative of y with respect to x. That means that you got to take the derivative. I'm going to put this a little bit more spaced out here. Hold on, like that. You got to take the derivative of this whole thing here, okay, with respect to x. That means that you got to take the derivative of this with respect to x. But here's a problem. You see, if you say that u equals g of x, that means that f from now on is going to be a function of u. For example, let's just say that g of x is x squared plus 1 minus 5x, whatever. You can see that g is a function in terms of x because x is the independent variable and g of x is going to be the dependent variable, okay? Now, here's the thing. If you're going to replace g of x for a u function in f, that means that f from now on is no longer going to be a function of x. It's going to be a function of u. That means that f is going to be in the format like 1 minus u squared plus 7 divided by 3 squared to the 5th of u to the third. You see, it's going to be a function of u, not of x. Now, you want to take the derivative of f with respect to x. So you want to take the derivative of this stuff with respect to x, but you don't have any x in here. So what if you're going to do this, okay? Since this is is a function in terms of u, so what you're doing here is doing du dx. But the problem is that if you're going to take u as a constant, because there's no x in here. So since there's no x in here, you can say that this term does not depend on x. You can say that this term does not depend on x, and this term right here does not depend on x. So if it doesn't depend on x, they're constants, right? So when you take the derivative of this stuff in here with respect to x, this one's going to become 0 minus, this one's going to become 0 plus, this one's going to become 0, because they don't change as x changes. But here's the thing, u is not a constant. Actually, u is a function of x. So when x changes, u is going to change. And when u changes, you can do something about this stuff. What can you do? Well, can you take the derivative of this with respect to x directly? No, because there's no x in here. But I'll tell you what you can do. You can do this. I'm just going to do something here. I'm just going to space this out a little bit more. Okay. So what you can do is take the derivative of this stuff with respect to u, and then you take the derivative of du with respect to x, because u is a function of x. You see here? Okay. Now, here's something that I disagree with many mathematics books, that they say that this looks like a multiplication of fraction right here. So you got f of u divided by du times du divided by dx. Okay, and they say that these are just the variables of differentiation and integration. Integration is the opposite of differentiation. I'm still going to teach you guys about that later. It's like when you add something, what's the opposite operation? It's subtraction. When you multiply, what is the opposite operation? Is division. When you differentiate, what is the opposite operation? Integration. So differentiation, integration, differentiation, integration, addition, subtraction, multiplication, division. Okay, one is the opposite of the other. One cancels the other. Okay, so mathematics books say that this is just a notation, that you cannot do this. You cannot cut these two here. Okay, I disagree, because you see, du is a very small difference. Remember what du is? If you don't remember, you got to go back all the way to beginning of my classes in this course. And you got to remember that du is a very small difference in u. When this u in here changes just an infinitesimal amount, what is going to be the infinitesimal amount of change that's going to happen to f of u? Okay? Now, f of u is going to change as u changes. But u, since it's a function of x, because u equals gx in here, okay, a small change in x is going to produce a small change in u, and a small change in u is going to produce a small change in f of u. So you can see that f of u actually depends on x. All right. So they say that you cannot cut these and see that in the end you are deriving f of u with respect to x, just not directly. You're using the chain rule. They say that you cannot cut these two, but I say that that's exactly what you're doing. Okay, that's exactly what you're doing. of course, you can't do that directly, because if you do this directly like this, you know, it's not going to work because you don't have any x's in here. So unless you already know beforehand that u is a change of x, you're just going to zero all these out. This is going to be 0, 0, 0, and that's not what you want. Okay, so this is the concept, the idea of chain rule. Now I'm going to show you guys something fun here. Let's go. You see, for example, I'm just going to give you some examples. I'm not deriving yet. I'm just going to give you some examples. So you have, for example, y equals the square root of x squared plus 1. You can see that x squared plus 1 is a function, and the square root of whatever is inside is another function. So you can replace this stuff. You can think of x squared plus 1 equals actually of u, and this y is the square root of u. So you can see that y is actually a function of u, okay? And u is a function of x. So how do you differentiate this stuff? Well, the way to differentiate this, like I told you, I'm just gonna drag these things down. I mean, I run on a screen real estate so fast in here. Okay, so can you do this y dx? Okay, if you do this, then you gotta differentiate this with respect to dx, and you can kind of do that, but you see, you're having two functions here with it looks like just one function, square root of x squared plus 1, but no, x squared plus 1 is one function, and the square root of anything that's inside, that's another function. So you don't want to do that directly, okay? Actually, what you want to do is derive. You want to do this, dy du dx, okay? So let's try to do that. Let's try to do that just for fun. I'm going to differentiate this whole thing, all right, using the chain rule. So what is u? U is, square root of u is u to the half, okay? So differentiating this, because it's going to be u to the half like this, guys, okay? Sorry, like this. So differentiate this stuff. What do we have to do? We have to do dy du and du dx. So dy du is just going to be half of u to the minus 1/2, right? Because you got half minus 1 half. Okay. Times, so I already differentiated this with respect to u. I already did this part. Now I want to do this part, du dx. What is u? U is x squared plus 1. So you want to multiply this by du dx, which is just what? 2x, okay? And then you're going to think, okay, so this is weird because I'm going to cancel these two in here. So what are you left with? You're left with u to the minus half times x, okay? But this is messed up. Now you have two variables here. Well, guess what? U equals x squared plus 1. So all you got to do is to say that this is actually, well, since it's to the minus 1/2, this whole thing equals x divided by the square root of x squared plus 1. Okay, this equals that. Because this x is in the numerator, I just repeated it here. Okay, and then you have u to the minus half, so you put it in the denominator to be u to the half. Now, what is u? U is x squared plus 1. Since it's half, it's the square root. So it's the square root of x squared plus 1. And there you go. So in order to differentiate this stuff in here, you have to do, this is the result. Okay, the differentiation of this is this. Now, can we do that? When differentiations get too complicated, you want to use many chain rules. Like you're going to have a u function, and then you're going to have a z function, and you may have a t function, they may have an omega function and a k function. You may have all kinds of functions. But this is kind of simple, so we're going to try to do that straight. like implicitly differentiating with respect to u and u with respect to x, but without making all this mess. You start recognizing these patterns as you go along, okay? So what do you have in here? Look, you got an inside function, which is this one, and the outside function, which is the square root. So let's do this. You always start differentiating the outside, okay? It's from the outside to the inside. It's not the other way around. So you differentiate with respect to the outside function. So you got the square root of something, okay? So you have something to the 1/2. You got to differentiate this. So let's do this. It's going to be differentiating it. It's going to be 1/2 of what? Of x squared plus 1 to the minus 1/2. Okay, you got this. Times the derivative of what's inside, which is 2x. And there you go. Now this 2 is going to cancel with this one. And what are you left in the end? You got x divided by the square root of x squared plus 1. It's the same thing here, okay, that I had done before. I know that I keep erasing and you can't compare it, but go back in the video and you're going to find out that this was the outcome before. This was the result, and now you got this result in here, and they're the same, okay? It's because these simple functions, you start recognizing things, you know, as you get more experience doing this, you're going to start recognizing that you can just do that and it works. It's like becomes second nature. Let's see here. For example, y equals, y equals the sine of x. What is the differentiation of this? Is the cosine of x, right? But look, it's because x is already in here. I'm going to show you guys something. Y equals, you're already applying the chain rule in here and you don't even see it. Sine of 6x. When you take the derivative of this, you got to see that this is actually, y is a function of u, okay? This is actually the sine of u, and u equals 6x. U is a function of x, and y is a function of u. So you got to do dy, du, du, dx. But let's do it a little bit faster for these ones. Okay, so what's going to be this here? The outside function is the sine, and the inside function is the cosine. So worry about the outside function first. Okay, so what is the sine of whatever? It's the cosine of whatever. So you do this, cosine of 6x. But now you got to differentiate the inner function with respect to x. Now, what is 6x? The derivative of 6x with respect to x? It's 6. So you multiply this by 6, and that's the answer. It's 6 cosine of 6x. That's the answer to the differentiation of this thing here with respect to x, which of course we're not doing directly. We're actually doing y du dx. Now y du is this part. This is y du. Du dx is this 6 right here. Okay? Now let's keep going. Let me see if I got another simple example here. Okay. Y equals 3x plus 2 to the 5th. Okay? So differentiate that. 3x plus 2 to the 5th. Alright, so the outside function is the 5th. And the inside function is 3x plus 2. Do that. It's going to be 5, 3x plus 2 to the 4th. Okay? Times the derivative of the inside function, which is just 3. So it's 15, 3x plus 2 to the 4th. I just want to recap this again. What do you have here? I'm just going to make a crazy symbol here. It doesn't matter. Okay? You have square to the 5th. So this is the outside function. So you take the derivative of this stuff. What is it? Differentiating this, you're going to have 5 square to the fourth. You differentiated this. But now you got to differentiate the square itself. And that's where this 3 here comes from. Because you're differentiating the square is the inner function. Okay? So differentiating 3x plus 2 is just going to have 3. Okay? Because the 2 is a constant, is going to be 0. So there you go. Another example, let's see. Y equals x plus the tangent of x squared. It's not the tangent squared of x, it's the tangent of x squared. Okay, so differentiate this stuff. It's going to be 1 because the derivative of x in here is 1, this x, plus the tangent is the outside function and the x squared is the inside function. So you got, what's the derivative of the tangent? Is the secant squared. Secant squared of what? Of x squared times the inside function, the derivative of the inside function, which is 2x. And there you go. So it's 1 plus 2x secant squared of x squared. Yeah, there's something else that I want to show you guys, that you're using the chain function even before you knew that you were using it. For example, y equals the sine of 6x, right? So let's do this. It's going to be, the differentiating is going to be the cosine of 6x times 6. Great. What is this? Cosine is the derivative of the outside function, which is the sine. The 6 is the derivative of the inside function, which is 6x. Great. Now, I'm going to show you guys that you were using the chain rule even before you realized it, even before you even knew that you were using it. Y equals the sine of x. Differentiate it, okay? What's the outside function? Is the sine of x, and the inside function is the x. So let's do this. It's going to be the cosine of x times the differentiation of the inside function, which is x. So what is the derivative of x with respect to x? Is 1. Okay, so you put a 1 in here, and there you go. It's the cosine of x. So you're already using implicitly the chain rule without even realizing it. Okay, it's because before we were just doing like y equals the tangent of x. And then when you differentiated it, it went like, okay, it's the secant squared of x. Yeah, but you see, the function itself is not the tangent. The function with respect to x. So the x is only here. X is the inner function and the tangent is the outer function. So when you differentiate it, you're differentiating the outside function first, which is the secant squared of x. Okay, differentiating tangent, secant squared. But you're using the chain rule here too, times the differentiation of what? Of x, which is just 1. And the secant squared of x times 1 is just secant squared of x. And there you go. You were already using the chain rule before you even knew it. Let's see if I want to talk about anything in this. Okay, let's see more examples here. Y equals 1 to the x plus 1. So, differentiate this stuff. Well, this is going to be very simple, but differentiate it. I'm going to give you guys some time to get started. Okay, so let's do this. You see, the 1 divided by the denominator is actually the outer function, and then you have the x plus 1, which is the inner function. So this equals x plus 1 to the minus 1. So whatever to the minus 1 is the outer function. Okay, this exponent here is the outer function. And the whatever in here is the inner function. So, so you could say that x plus 1, if you wanna, it's the last time that I'm doing this for now, but just for you guys to be straight, y is going to be a function of u. So you say that this is 1 divided by u, and u is a function of x, which is x plus 1. So dy, you do dy du, because y is a function of u, du dx, okay? Because when you cut these two, you're not going to cut them, but if you cut these two, what do you have in the end? Dy dx, which is what you want. So let's do this. Dy du, well, this is going to be u to the minus, so differentiating that with respect to u, now with respect to x, you have minus u to the minus 2, all right? And now you want to do du dx. Now what is du dx here? Differentiate this. Du dx is just going to be 1. So actually you're multiplying this to 1, which is just equals minus u to the minus 2, which is minus 1 divided by x plus 1 squared. Okay, this is in the numerator, so when u comes to the denominator, the exponent changes sign, and u equals x plus 1, so I put the x plus 1 in here. Okay, so let's try to do this directly here. You got this, so you differentiate the outer function and then the inner function. So this is going to be minus, I'm just doing the same, but a little bit faster, minus x plus 1 to the minus 2 times the derivative of the inner function, which is 1. So this equals minus 1 to x plus 1 squared. You see, this and this are exactly the same. It's just that when things get too complicated and you have to replace these functions here, I've seen integration, which you're going to do later, and differentiations, but especially integrations, when you have to substitute like, I don't know, 15 times. So you don't have just a u function, you have a y and u and z, a, b, c, d of the entire alphabet, okay? And you're just going to keep replacing, and after you integrate or differentiate the whole chain, you start back substituting, okay? So what was y? Y was this, and what was u? U was this, and what was omega? Omega was this, and what was the k function? The k function was this. So you keep back substituting, back replacing, and in the end, you're just going to see an entire huge function of x. Let's keep going, because practice makes perfect, right? At least that's what they say. I know this is kind of simple, sine of 2x. So differentiate this is going to be what? Cosine of 2x times 2, right? So differentiating sine becomes cosine, and the sine of, and the differentiation of 2x is just 2, so there you go. Square root of 3x squared minus x plus 1. Differentiate that. You gotta remember that this is the inner function, okay? So it's gonna be half times 3x squared minus x plus 1 to the minus half times the derivative of the inner function, which is what? 6x minus 1. Okay? So what are you going to have in here? Let's just put this in the right order. I mean, put it in the right format, because I think this format is ugly. So it's going to be 6x minus 1 divided by, you got to multiply a 2 in here, and here's going to be the square root of 3x squared minus x plus 1. And that's it. This is the differentiation of this. Okay? Let's try another one. Yeah, now we're going to use the chain rule 3 times. Okay, y equals tangent squared of x. So you see, this becomes complicated. So let's just say that y, because you got a function here which is the x, the middle function is the tangent and the outer function is the square. So let's try to do this here. First I'm going to do it slowly and then I'm going to do it straight, okay, from the outside in. So let's make a mess here, I don't know. You can say that u equals the tangent of x. And then you can say that z equals x. Okay, and y becomes a function of u. So you can see this, that this is actually y is going to become a function of u. So it's going to be u squared. Okay. Yeah, it's because I already have an x in here. So yeah. You know, just to have a point, I'm going to put a 3 here. So you put a 3 here and you got to put a 3 here. Okay, so u is the tangent of 3x, and you got the tangent of 3x in here. So this is a u squared, okay? But you see the tangent, actually it's a z, so you can also say that this tangent of 3x equals the tangent of z. All right, so what you got to do is to do the first thing that you're going to do is the square here, okay, and becomes a square of what? Of the tangent of 3x. The tangent of 3x is u, okay, so you're going to do this. You're going to differentiate y first with respect to u, and then you gotta let me think here. Dy du, okay, and then you want to differentiate. Okay, yeah, because the third function is this, y equals u squared. Okay, so y is a function of u is a function of tangent. A tangent of what? A tangent of z. Gotta put a z in here. That's why when a function is relatively simple like this, you just want to do all the substitutions automatically in your head without going through this scheme here. So y is a function of u is a function of z, and z is a function of x. So going from the outside to the inside, okay, is going to be dy du. U is a function of z, so du dz. And z is a function of x, so dz dx. You can see that in the end, what you want to do, because what is the original format? It's this one. So this is going to be you want to derive this with respect to x. Okay, so look at this. You cut this one with this one, and this one with this one. What are you left with? Dy dx, which is what you want, right? So let's do this very slowly. Dy du, okay? So you're going to have 2u, that's it. That's dy du here. Now you want to do du dz. Du dz is going to be the secant squared of z, okay? And then you want to do dz dx. Dz dx is 3. So you put a 3 here. And in the end, you're left with, now you want to back substitute. That's what I'm talking about. 3 times 2, 6. 6u. What is u? Is the tangent of z. And what is z? Is 3x. So you want to do 6u, which is the tangent. but the tangent of what? Of z, and z is 3x. Okay, so you already took care of this. The 6 comes from 2 times 3, so you got u here. Now you got the secant squared of z. What is z? 3x. So this is the entire differentiation right here. Now what I'm gonna do is to just bring this down. Okay, I'm gonna bring this down here so we can compare it with the thing that we're gonna do automatically here without the little skim. We're gonna do it from the outside in. So the outside function is the power 2, the inside function, an inner function is the tangent, and the innermost function is the 3x. So let's just do this from the outside in. We're going to do 2 times the tangent of 3x times the derivative of the tangent, which is the secant squared of 3x, times the derivative of the inner function, which is 3. So here we go. 3 times 2, you got a 6. And then you have the tangent of 3x, okay, secant squared of 3x. Now look at this. 6 tangent of 3x, 6 tangent of 3x, secant squared of 3x, secant squared of 3x. These are exactly the same. But you see that it was a lot simpler in here. Okay, so when this becomes second nature to you, you don't want to make this little scam in here. You don't want to do that because it's just going to confuse you. Right? You can see that these two are the same. Compare them. 6 tangent of 3x, 6 tangent of 3x, secant squared of 3x, secant squared of 3x. The same stuff, guys. I don't know if I want to keep going. Maybe one more example before I shut this thing down. So let's do this. You got 3x minus 2x squared. And you got a 3 here, and you want to derive. Let's do this directly, okay? So it's going to be 3 times 3 times 3x. Holy cow, man, that's a very ugly minus in here. Minus 2x squared to the power 2. So 3 times 3x minus 2x squared, okay, times the derivative of the inner function, which is 3 minus 4x. And that's it. There you go. You don't have to multiply it out. You know, you don't have to expand this binomial thing here, this term, and then multiply by this. You just have to show it. So it's going to be 3x minus 2x squared times 3 minus 4x. That's it. Yeah. Okay. Let me see here. I don't know if I want to go for another one. Let's see if I want to do this now. You have the cube root, or the cubic root of x squared minus 1 squared. So let's differentiate this. You got to see that this is x squared minus 1 to the 2/3, right? You know this, right? This differentiating, I just want to show here. This is x squared minus 1 to the 2/3. Okay, so this will be 2/3 x squared minus 1, and then you got 2/3 minus 1, that's going to be minus 1/3. times the derivative of this, which is just 2x. All right. So in the end, putting this in a beautiful format, what you got is 4x divided by 3, and you got a cube root in here of x squared minus 1, and that's it. You know, I think it's gonna be enough for today, guys. I'm not gonna keep going. All right, see you guys in the next video.